Hi, Taylor here. Today we're going to be walking through question 19. Let's jump into it. Observe a random sample x1, x2, to xn from a continuous uniform distribution ranging from 0 to beta. Beta hat is equal to the maximum of x1, x2, xn is chosen as an estimator of beta. 1. Beta hat is both the maximum likelihood estimator and method of moments estimator of beta. 2. Beta hat is sufficient statistic for beta. 3. The minimum variance unbiased estimator of beta is a function of beta hat. Determine which of the above statements are true. Okay, so to start off, I'm going to be referencing this in the answer, but I definitely recommend doing question 18 first, or going to my previous video walking through question 18. I'm pretty sure that when they were setting up this exam, they kind of, or maybe it was just happenstance, but I think they might have intentionally placed question 18 before question 19 because it gives you a way to kind of quickly approach this problem. Otherwise, this question would feel a little out of left field, I think. But background required knowledge, again, a lot of this is in the previous question, is method of moments, maximum likelihood, sufficient statistic, and then here I have two quotes concerning the minimum variance unbiased estimator. So namely that if something is to be the minimum variance unbiased estimator, it is 1, unbiased, and then 2, can be written as a function of the sufficient statistic. So if you have a sufficient statistic and can write some function using it that produces an unbiased estimator, then you know you have the minimum variance unbiased estimator. So jumping into the problem, first we had that beta hat is both the maximum likelihood estimator and the method of moments. This is not true because the maximum likelihood estimator is just the maximum observed value of your sample, whereas the method of moments estimator is taking the average of your observed data and then multiplying that by 2. And obviously that is not necessarily equivalent. So that's not guaranteed, and so we know that 1 is false. 2, beta hat is a sufficient statistic for beta. So again, this was in the previous problem. So if you want to see a walkthrough of that, please go to that video. But just that the maximum observed value is the sufficient statistic, and that's exactly what they have to find here. So point 2 is true. The new bit of information coming into this problem is 3, which is what is a minimum variance unbiased estimator. So for this problem, if you need to either just have this memorized or know this property and then do a bit of math. So what we can do is consider what is the expected value of the maximum, and then can we, using that, and this is because the maximum is the sufficient statistic. So can we get an expected value of the maximum of a data set, and does that translate directly to something having to do with the true parameter value? So I'm just not realizing this. I'm using theta instead of beta, but just pointing that out. So first off, what is the CDF of the maximum of a sample? Well, that's the probability of seeing an x less than a specific value all n times. And we want the PDF, but we're starting with the CDF because this is just a much easier thing to write out. And then we can say, okay, well, the CDF of a uniform going from 0 to theta is just going to be x over theta to the power n is the CDF of the maximum of a sample. PDF is just taking that derivative, so here derivative with respect to x gets us this, so carry down the n for the x, and then x to the n minus 1, and then the theta gets left alone because it's just a constant. Then to get an expected value for the maximum, we can take its value multiplied by its probability. So we're just taking that probability weighted average, ranging from 0 to theta of all possible values it could be. So you can pull out the n theta to the negative n, and then all you're left with is x to the n, and that's because it was x to the n minus 1, but we multiplied by x, so that just goes into the exponent. You can then take the antiderivative and plug in values ranging from 0 to theta, and so that's how we get this here. And then the 0 just goes away, and we're left with, let's see, so this theta to the negative n multiplied by theta to the n plus 1, the n and the negative n cancel, so you're just left with theta in the numerator. You can bring the n into the numerator as well. So we now know that the expected value of a sample maximum from a uniform distribution is just equivalent to n theta over n plus 1. But the question is, can we write the true value of our parameter as the function of just our sufficient statistic? And we can by just inverting this, right? So we're going to multiply both sides by n plus 1 and divide by n. And here we can see that an unbiased estimator would be our using that maximum. So a sample maximum increased by a factor of n plus 1 over n will have an unbiased estimate. So we know it's both unbiased and it's using the sufficient statistic, which we determined in question 18. And those are the two requirements for it to be a minimum variance unbiased estimator. So this is just me copying the bullet point from above. So with all that said, just to reiterate, the minimum variance unbiased estimator of beta is a function of beta hat, which it is. And since we know that 1 is false and 2 and 3 are both true, we know that the solution is D. Thank you for watching. If you enjoy these videos or find them helpful, please consider subscribing. Thanks.